The idea of logarithms comes from, I guess, one place it comes from is because it is the inverse function of the exponential. Now, we haven't talked about inverse functions, so let me just briefly touch on that. An inverse function, what it does, one thing that it does, is it just switches the role of the x and the y. For example, if I have y equals x squared, very simply, the inverse function, what it does is it flip-flops the x and the y. And so the inverse function of that would be x equals y squared. Just wherever there's an x, put a y, and wherever there's a y, put an x. In this case, there's just one of each. But that's what an inverse function does. And it, like I said, it doesn't, if you've got more than one x or more than one y, same thing. The inverse, what would the inverse here be?
X equals y to the third minus y to the second.
X equals y to the third minus y to the second? Yeah. And so that very simply is the way you can get an inverse function for a function. It just swaps the roles of x and y. And there's other things, and we'll talk maybe a little bit about more of those things, but that's the inverse function, and it can be helpful to know that. And in this case, it does help us with solving exponential functions for one thing. But anyway, logarithms are the inverse function to the exponential function. Now, so if I've got an exponential function, y equals, all right, let's just say it's a to the x, right? That's our basic exponential function, right? We talked about those last time. Looked at the graph, looked at some applications a little bit. That's an exponential function. So the inverse function here would be what? Well, just swap the role of x and the y, yeah. X equals a to the y. All right, now, that is one form of what we call the logarithm, or a form that we'll adjust to, but the problem here lies in, where the y is. It's that's a little difficult because, we usually like, we like y equals equations, and we could say the same thing over here. To get those in y equals form, that one, we could do a little bit and get that one in y equals form, right? Square root both sides, plus or minus. That one would be a little more challenging to get y equals, but this is one form of the logarithm. Now, the actual definition, here's what the definition, so keep that in mind. But that's the inverse function there. And the definition of logarithm actually involves that little expression right there. The logarithm base A. So logarithms, they also have a base, and it's A, like, we think of this as base A, the thing we go to a power, but logarithms also have bases, and we'll show, this is what, it'll show where this base goes. You write the logarithm. The logarithm base A of x, of some thing, is log base A. So the base A goes, it's a little subscript on the log, log base A, and then the x, what we're taking the logarithm of, goes beside that. So log base A of x is what that is. Equals y, which is just a number, the value of the logarithm, if and only if a to the y equals x. So this is how the definition, or how we're defining logarithm in this particular case here. Log base a of x equals y. So yeah, this is just, this log notation, it's just a way of representing what we just talked about is the inverse function of the exponential. Isn't that the same thing that we said was the inverse function right there? Yeah. Okay, so that's what a logarithm is. Now, the way we kind of keep these two straight then, so there's a connection between these two. I usually call this log form of a logarithm for obvious reasons. And this is exponential form of our logarithm right here. It's kind of the conversion. And that's where we'll start. We'll just convert from one form to the other. To start us off here, if you haven't dealt with logarithms before, it's a little, takes a little getting used to, but it's not too bad. All right, now there are with logarithms, and another reason for logarithms, like I said, because it's the inverse function of the exponential, we're going to use it to solve some exponential equations. It'll help us solve exponential equations in a few days when we talk about that. But it also has application in and of itself. The magnitude of earthquakes, that formula, it's based on a logarithm. It's a logarithmic formula. Models with human memory somehow are involved, logarithms. There are applications that do involve a logarithm, and sometimes in sciences, I know they do a logarithmic scale, the y-axis in a logarithmic scale, so different applications of it.
Computers.
Computers maybe? Okay. Anyway, so let's talk about, get kind of used to these logarithms here. All right, so first of all, let's change some logarithms to that exponential form. So change to exponential form. Number one. Oh, I forgot. Before we do that, I got to talk about the applications, and I forgot. There are some restrictions on this. Logarithms do have restrictions. The big one, the main one, I guess you might say, is that x, the value of x, you cannot take the log of a negative number. We're talking about real numbers here. You can't take the log of a negative number. So the way we can state that is x up here in this definition, x cannot be a negative number, or 0 either.
So greater than equal to 1.
It has to be greater than 0. It can be a fraction. So yeah, x has to be greater than 0. That's another way to put that. Okay, x has to be greater than 0. So it has to be positive. The a also has to be positive. The base, in other words. And matter of fact, a has to be positive also. And it can't be 1.
It can't be 1?
Cannot be 1.
Could it be a half?
Can
it be a half, or it has
Yeah,
to be greater?
it can be anything positive, just can't be 1, besides 1. So yeah, the a can be fractions, but it can't be negative, and it won't be 1 either. So, and you'll see why, a few of those reasons in just a second. All right, but this is the big one right there, x, because we'll come across that in several different problems. Yeah, your x can't be negative or 0. All right, so let's do a couple just to see how it works. Change to exponential form. So this is the log base 4 of 64 equals 3. So we want to change that to the exponential form of the logarithm. All right, and so yeah, you just follow the pattern here. This is the base of the logarithm. Well, it's also the base of the exponential form, right? So that's where the a goes. So the a here is 4. All right, then that, in exponential form, that base gets raised to the power. And in this case, the power is right here, right? That's the y, that's the a, and that's the x. So exponential form is a to the y equals x. And so exponential form of this is 4 cubed equals 64, which that's a good statement right there, isn't it? Doesn't 4 cubed equal 64? 4 cubed equals 64. So yeah, so this is definitely a true statement here, and that's how it is represented as a logarithm. Is that okay? All right. Number 2, same deal. Let's do this. Log base 3, 1/9 equals -2. See that this is true as well. So what's the exponential form of that? Well, again, the base is here, so that's the a. This is the x. And this is the y. So what do we got here? A to the y. So 3 to the -2 equals 1/9. A to the y equals x. That's the exponential form. Okay? Which also is a true statement, isn't it? 3 to the -2. We talked about negative exponents last time. Yeah, 3 to the -2 is 1/9 because you flip it over, square it. All right? Okay. Well, you can go the other way too. I think they have you do a couple of these in this assignment too. So let's go the other way. Change to log form. And that's number 1. 7 cubed equals 343. And so I want to write that as log base a of x equals y. So what's the a, what's the x, and what's the y here?
A is 7.
Yeah, this is, a is the 7. What's the 3?
The y.
That's the y, and this over here is the x, isn't it? In logarithm form, in the logarithm, it's a to the y equals x. And so change it to log base a of x. So it'd be log base 7 of x, so that would be of 343, and that equals y, which is 3. Okay? So it goes pretty much same way there. Okay? All right. Now, so how does this work, or how does this help me, or what can I do with this? Well, yeah, so the next step here is let's evaluate some logarithms. And it's basically, the way I approach it is basically the same way as we did these first two here. Evaluate logs. All right, number 1. All right. Yeah, what you have to realize here is when I have a logarithm, it's just a number. If I have, the base and the number, there's a number inside there. When I take the log up, if those are numbered, this is just this just has a value. This is just a number. This equals something, and that's how I talk about it. Is so this is just a number. I don't know what it is. Question mark. What is that? Equals, and then if I think of it that way, then I could just convert that to exponential form, couldn't I? So go to exponential form for this. Exponential form would be, this is the a, this is the x, this is the y, so it's a to the y equals x. So I've got 4 to what power equals 16, don't I? Yeah, 4 to what power gives me 16. And so the value of this logarithm is going to be what power of 4 gives me 16, which would be obviously 2, yeah. So this logarithm is 2. Okay. All right. How about log base 3, 243? Well, again, that's just some number I'm trying to figure out. Exponential form then, to kind of explain why this logarithm is what it is, 3 to what power is 243. Which brings up the point, you may not know what power of the number gives you that, but just try different powers. 3 squared, 3 to the third, 3 to the fourth, 3 to the fifth, because these are going to be nice. We'll talk about ones that are not so nice powers, but did anybody figure it out? What power? 5, yeah. So the power here is 5. It takes 3 to the 5th power to get 243. So that's the value of the logarithm. It's 5, okay? All right. Now, one thing that some like to point out here, or note, it helps some, is what is this value in essence then, in both cases here? What are we looking for? It's a power, isn't it? I'm looking for the power of this that gives me this. That's what the logarithm is. This value here is the power of this that gives me the 16. Or the power of 3 that gives me the 243. So a logarithm it's a power. It's an exponent. The value is an exponent. That can help you do that. Okay, so we did that. So number 3, log base 3 of 181, 1 over 81 is what? Well, again, what does it mean? 3 to what power gives me 1 over 81?
It's going to be negative.
It's got to be a negative power. All right. So yeah, 3 to the 4th power gives me 81. But this is the flip, the reciprocal of that, the flip of that. And so how do I get it to be 1 over 81 instead of 81? Like you said, make it a negative power. Yeah. So the power here needs to be negative 4, doesn't it? The 4th power gives me 81. The negative 4 makes it flip over. So this this logarithm is negative 4. Okay. All right. Let's talk about some other types of values here. All right. So we saw that one. We got a negative value for that logarithm. What about this one? Well, if we set it up like we've been doing, I'm looking for what power of 5 gives me negative 25. Is there a power of 5, talking about real numbers, that gives me a negative 25?
No, because x can't be negative.
Okay. All right, this explains why the x can't be negative here, because what are you going to put here? Positive 2 gives me positive 25. If I do negative 2, I get 1 over 25. There's no way to get a 5 to a power to give me a negative 25. So yeah, this is no solution here. Undefined, or not a real number, something like that. Probably a better way to say it. There's not a real number that can happen. Yeah, and so exactly, that's why right here, this is our x, isn't it? And what do we say x has to be? It has to be a positive number. It can't be 0, and it can't be a negative number, okay? And this is why, because it just doesn't work out. The numbers don't work out, okay? All right, does this one work? the log base 5 of 1. Gonna do that one?
X can't equal 1.
X can't equal 1. A can't be 1. X can be 1. Yeah, the A can't be 1. The X can't be. X can be 1. 5 to what power gives me 1?
0.
That's 0 power, isn't it? Yeah, so this one can be done. The value of it is just 0. That logarithm has a value of 0. All right, one more. Log base 7 of 0. Was what? 7 to what power? Is there a power of 7 that equals 0? There is no power of 7 that equals 0. This is not a real number either. And again, this explains it, because what power of 7 are you going to give me that gives me 0? There's not a power of 7. 7 to the 0 is 1. You can get fractions. 7 to the negative 1 gives me 1/7, but you can't get equals 0. So power of 7 equals 0. So yeah, that explains again what we just talked about. When I've got a logarithm, log base A of an x, the x can't be negative and it can't be 0. And this is why, because you just can't get a logarithm equal a power of that, a power of A that gives you that value. Okay? Let me do one more. Just saw it on my paper here as I was doing that one. A little tricky one are these, log base 64 of 8, because it's kind of flip-flopped of what we would normally expect here. And we may have not even talked about this fact here. What power of 64 gives you 8? Well, if you recognize it there, 8 is the square root of 64, right?
Would it be like 1/8?
Well, it turns out your square root of any number, call it k, the square root of k can be written as k to what power? It's 1/2. It's the half power. A square root can be written as 1/2 power. A cube root is 1/3 power. Okay? So, what I'm saying here is, yeah, I need to square root 64 to get 8, don't I? So what power of 64 gives me the 8? It'd be the half power, yeah. Because that's the square root. So anyway, I think there used to be a problem with that in it, so you might have to go to a half power there. Now, there's those restrictions. One more thing on this. There's those restrictions. X can't be negative or 0. What about the y? Did I have any restrictions? Did we mention any restrictions on the y? No. Y here, it can be negative, it can be 0, it can be a fraction, 7, right there. It can be a positive. Y can be anything. Y can be positive, negative, fraction, 0. It's just that the x can't be negative or 0. Okay? All right.